All right, what did I mean by covalent interaction? When I think about a bond is going to range from covalent to ionic. And so, is there a distinct cutoff? No, we have bonds that range from non-polar covalent to polar covalent to ionic. What's the difference between those bonds? Well, the difference is we could see in a chart like this. Do you guys remember what delta En stands for? The difference in electronegativity. And so the bigger the difference in electronegativity, the more ionic or the less ionic the bond. The more ionic, right? And so the bigger the difference in electronegativity, the greater the percent ionic character of the bond. And so we expect some bonds to be 100% ionic up here, let's say. Let's say there's no difference in electronegativity. The difference is 0. Then we expect that to be covalent, non-polar covalent. So this should be 0% ionic. Actually, I should just write that at the origin here. And then we're going to have everything in between here. All right, that's based on just the difference in electronegativity. Is this trend perfect? No, this trend's not perfect because when you look at the data scatters all over. Remember we were talking about R squared? Do you guys know R squared? Have you heard of the term R squared before in statistics? What's R squared referred to? R squared is called the correlation factor. And so, the data is kind of scattered and we just see a general trend. The general trend looks like this. And so there are things that have, a smaller delta En but are quite ionic. And there are things that have a bigger delta En but are more covalent. Does that make sense? And so what causes those deviations? What causes those deviations are, the orbitals that are involved and how they bond and this kind of stuff. What makes up a covalent bond? We have valence bond theory is orbital overlap. That makes up the covalent bond, how well the orbitals overlap. Even in MO theory. MO theory, we do linear combinations of atomic orbitals, and when you get good orbital overlap, then you should form good molecular orbitals. Does it make sense? From MO theory. And so, what I meant here for PBI, when we look at PBI, or actually let's do PbCl4. When we look at PbCl4, this should be highly ionic because it's lead plus 4, right? To make a strong ionic bond. You get highly charged ions like this, though, the covalent interaction is significant. And so what happens is this doesn't form ionic. This forms molecules. And that's because the bonding here is quite covalent. So this has a high covalent percent character versus PBI2 or PbCl2. PbCl2 is much more ionic. And so if we were to do the formula, there'd be a lot less sharing of the electrons. Here we're going to get much more sharing of the electrons. Well, why? Well, one is because of the high oxidation state on lead. 2, it's because these heavy metals usually have quite a bit of covalent character in there. And so even though I'm showing this is 100% ionic, there's still some covalent character in there. It's probably not 100% ionic. It's just much easier to draw things. If you're to draw something polar covalent, how do you draw it? No, we just draw it like a normal covalent bond, right? Sometimes we use dots to represent the distortion of the electron cloud. I'm using all this jargon that I use in Chem 1A, but does this make sense or not? If not, let me know. And I'll try to explain myself more. And so in something like PbCl2, we expect to form an ionic lattice. Well, what is an ionic lattice? An ionic lattice is we're going to have a whole bunch of ions packed together in the solid state versus molecular. a molecular solid, we have these molecules packed together in the solid state. Turns out PbCl4 is actually soluble in water, oddly enough, because you'd think, hey, that looks like tetrahedral, but the PbCl2 is insoluble. And so what I meant by percent ionic character or percent covalent character, it varies. Now, how could you have predicted it? We didn't. We just saw the data. The data shows that PbCl4 is much more, it forms these molecules. You know, when you do a structural analysis, you do structural analysis in different ways. You can figure out it forms this molecular. And so this is just based on observation. It's not based on any prediction that you did. You know? And generally, what you do find is for some of these very high charged oxidation states, there's quite a bit of covalent interaction in there.
What's the relationship between molecular geometry and solubility?
The relationship is this. You know, when you have polar bonds like this, you could still have a non-polar molecule. If all the bond dipoles cancel each other out in 3 dimensions, the whole molecule itself will be non-polar. If the molecule itself is non-polar, then it's not soluble in polar solvents. And so the classic example is CO2. CO2 has polar bonds, but it's non-polar because the bond dipoles are equal and opposite. If you have a tetrahedral structure, this looks like square planar, doesn't it? But if we had a tetrahedral structure, even if the bonds are polar, we expect it to be non-polar because tetrahedral are what we call spherically symmetric. And so even if they're bond dipoles, they would cancel each other out in 3 dimensions. And so the geometry is going to have an impact on things. But this is more trickier because, you know, this is soluble in water. Well, what makes it soluble in water? So we have to look at it in more depth. You know, obviously what we do is we try to apply as much, you know, theoretical knowledge to something that we can, but it's difficult because to properly do this, you have to do, you know, a full quantum mechanical treatment of it. And that requires like a computer and software and approximations and other things. And so sometimes we miss out on certain factors, which we'll talk about later. Other questions? Anthony?
Yesterday you were saying that if there's a solid on the reaction side and precipitate on the product side,
Yeah.
then we can't assume that that's a driving force?
You can't assume that's a driving force.
Is that the same when there's a gas and a gas, but 2 different gases?
Yeah, that would be the same. But there could, you know, when you have a gas and a gas, there are typically other things involved. And so those other things will tell you, all you need is one driving force. And so if you're going from solid to solid, but there's some other driving force that's not related to those solids, then that's enough. Then we'd say the reaction goes. We could still figure it out. You know, based on things like solubility. So if we have silver chloride plus bromide, this is going to be net ionic form. So let's say we add sodium bromide or something like that. Then will we form silver bromide and chloride? This is called a solid-solid conversion. So could we convert silver chloride into silver bromide by adding chloride to it? Well, it depends. It depends on which one's more stable. If silver bromide's more stable, then we should be able to do that. Well, how can we tell which one's more stable? We would look at its, what would we look at? Well, this is something we're going to look at later in the semester, but for right now, we would look at its Solubility. Solubility, you don't have those memorized, right? We could make a prediction based on Coulomb's law. Silver is a plus, chloride's a minus. Silver is a plus. These two silvers are the same size, but bromide is bigger or smaller than chloride? Bromide's bigger. Bromide's bigger. So which one's going to be harder to break apart? Silver and chloride or silver and bromide? Silver chloride is going to be harder to break apart. So we expect silver chloride to be less soluble than silver bromide if the bonding were 100% ionic. But is the bonding 100% ionic? No. There's some covalent interaction, and that screws up our prediction. Because if all we needed was Coulomb's law, then chemistry would be so easy, right? Because we could predict everything based on. Do you guys know Coulomb's law? You know, Coulomb's law just says the force of attraction is proportional to Z on bottom by A, Z on bottom, divided by the distance squared. So the charge on A, charge on B, and the distance between the center of the charges. If that's all we needed, and if everything was 100% ionic, then that's all we really need, and we'd be done with it. But we have these things called orbitals, and this MO theory, and this other stuff, which makes things a heck of a lot more complicated. And so, if this were ionic, we're done. No reaction. You know, silver chloride should stay, right? But because there is this covalent interaction, we have to think about that. And that could change things. Now, we're going to talk about this covalent interaction today, because it's part of today's PowerPoint. But let me give you a little preview. Let's see, because experimental fact is fact, right? Any theory we have has to agree with experimental fact. If theory and experimental fact conflict, then which one do we abandon? We abandon the theory. And so let's take a look at silver chloride. Silver chloride soluble in water. Oh shoot, this is only 50 degrees C. 520 micrograms per 100 grams of water at 50 degrees C. So remember 520 micrograms in 100 grams. CRC is better. CRC would have more temperature. 0.140 milligrams per liter. 0.140 milligrams per liter. Well, a liter is 10 100 milliliter portions. And so we'll divide that. And so in 100 milliliters, it'd be a tenth, so it'd be 0.014 milligrams. 0.014 milligrams is 14 micrograms, right? Just move the decimal place 3 over. So we got 14 micrograms per 100 milliliters at 20 degrees C versus 520 micrograms. Which one's more soluble? Seemingly. 14 or 520, the temperatures are different. But, well, 14 is less soluble, 520 is much more soluble. And so, you know which one is more soluble? Silver chloride's more soluble. And so what does that tell you? Should we abandon quantum mechanics? No, we don't. We don't abandon, but we should abandon this thinking that it's 100% ionic and it's purely electrostatic in this way. Yeah, there's got to be some covalent interaction. This covalent interaction pops up with these heavy metals. These heavy metals like silver, lead, mercury, have a significant degree of covalent interaction. And so, you know, our thinking ingrained in, you know, charge densities, sizes, this type of stuff, doesn't work so well for heavy metals because of significant covalent interaction versus our thinking for regular things. Let's talk about iron 2 hydroxide versus iron 3 hydroxide. Which one's more soluble? Both of these are insoluble, but which one is more soluble? You know, when we say insoluble, does that mean 100% insoluble? No. You know, a little tiny bit will dissolve, like a microgram or maybe even 100 micrograms. When you say something's insoluble, what do you mean? If you go back in Chem 1A and you look at the solubility rules, it means less than 0.1 moles will dissolve in a liter. 0.1 moles is a lot in a liter. So if you have something like that dissolves 0.95 moles in, 0.095 moles, we call that insoluble. But if you have 0.1, we call it soluble. Does that make sense? You know, it's such a black and white cutoff. No, it doesn't really. So we look at the numbers. And so both of these are insoluble, but they aren't insoluble to the same degree. Which one is more insoluble? Which one is more soluble? You know, I should say, which one's more soluble? And so we look, iron 2 versus iron 3. Do you know iron 3 is bigger or smaller than iron 2? It's smaller. It's got more charge. Now we got to break it off a hydroxide. Hydroxide. Which one is going to be easier to break off? A hydroxide separated from an iron 2 or a hydroxide separated from an iron 3? Iron 2 will be easier to break off, right? Because it's less attraction. This is going to be harder to break off. And so we expect iron 3 hydroxide to be much less soluble than iron 2 hydroxide. And you know what? That's right. That's right. Because these types of things are more, there's less of a covalent interaction here we have to deal with. And so heavy metals are a little more trickier to deal with than regular metals. In general. And so if we just had something like, you know, on one side we have iron 2 hydroxide, on the other side we have iron 3 hydroxide, then yeah, we could figure that out. Iron 3 hydroxide should be more stable, harder to dissolve, harder to break apart. Okay. Let me stop here.